So today we are going to discuss about the introduction to MOSFET, or you can say MOS transistors. So the ultimate aim of this subject is to realize the logic circuits using MOSFET. However, we cannot understand the level of design unless we are exposed to the basic of operation, or you can see theory or fundamental of the MOSFET devices. So in today's lecture, we are going to discuss about the MOSFET. So first of all, let us start with the question. What is MOSFET? What is MOS transistor? So a MOS transistor, let us talk about a MOS transistor. What is MOS transistor? So MOS transistor, a MOS transistor conduct electrical current, or you can say electric current, by using an applied voltage to move charge from source side to drain side of the device. Drain side of the device. So if someone asks you what do you mean by the MOS transistors, then you should answer in such a way that a MOS transistor conduct electric current by using an applied voltage to move charge from source side to drain side of the device. So I would like to ask you, what does the source and drain represent here? Anyone can answer?
The two terminals of MOSFET.
Two terminals of MOSFET, right? So in the last lecture, I also discussed about a MOS transistor is a MOS transistor is a majority carrier device, right? Majority carrier device. So I would like to ask here to Rajiv Agrawal, what do you understand by the majority carrier here? Yes, Rajiv, are you there? If you will not speak within a second, then I will also mark you absent. Okay, Sai Reddy, what do you mean by the majority carrier?
I don't know, sir.
You don't know. So you didn't attend the last lecture?
No, sir.
Okay. Bhavya Gupta, what do you mean by the majority carrier?
Sir, I don't know.
So you didn't revise the lecture what we have studied in the last class. Very good. So in the majority carriers means you will have to read every day. And like 2 days, I will ask you questions every day in every lecture about the last lecture. So majority charge carrier means there are two types of charge carriers. If we talk about the charge carriers, so here there are two types of charge carriers, that is minority charge carriers and majority charge carriers. So minority, in case of BJT, let us talk about the BJT, that is BJT stands for bipolar junction transistor, right? So in BJT is a bipolar junction transistor means it has both the carriers, that is minority and majority. Let us talk about the p-type semiconductor. So what do you mean by p-type semiconductor? So what are the majority carriers here in case of majority p-type semiconductor?
Holes.
Holes. Good, good. You should answer in such a way that I like it. Holes. And what were the minority carriers here?
Electrons.
Electrons. So here the electrons will be minority carriers, right? So if I talk about the BJT, in case of BJT, minority carriers and majority carriers, both play a role to conduct the electric current, right? However, in case of MOSFET device or MOS transistors, only majority carriers play a significant role in flowing the current from source side to drain side. Okay, got it? Okay, so based on the majority charge carriers, we can say that there are two types of MOSFET, two types of MOSFET, right? First, you can say N-type MOSFET, N-type MOS transistor. So, what does it mean in case of N-type MOS transistor? So, majority charge carriers will be
Electrons.
good. So, majority charge carriers, the majority carriers are electrons here, right? Good. What was the second point? Okay, so have you heard about the mobility term? In case of whenever you have studied about the semiconductor, say yes or no, so that I can so that I can explain about
Yes, sir.
Yes, sir.
mobility, right? So in case of electrons, they have the higher mobility, or you can say greater mobility. So what do you mean by mobility? Mobility is represented by mu. Good. So if I talk about the electron mobility, it means that electron mobility mu n. Okay. If I talk about the hole mobility, then it means that mu h. Okay. So I mean to say that what do you mean by mobility? That is mu. What does it indicates? It indicates that on the application of electric field, how fast the charge carriers can move from one side to another side, right? On the application of electric field, how fast the charge carriers can move from one side to another side, right? So what does it mean? So mobility, so the speed of the charge carriers depends on the applied voltage, right? Yes or no?
Yes.
Sir, it should be V drift upon electric field.
Okay,
Mobility.
okay, good. VD
Drift
upon E,
velocity.
right? Okay, VD upon right. Good. VD upon E, right? So VD upon E, it means that the drift velocity, where VD is drift velocity and E is the electric field. What is the unit of electric field? It is measured either in volt per meter, or you can say volt per centimeter, right? So VD is equal to mu multiplied by E. So what is the unit of mobility then now? Yes. Okay. If for what is the unit of speed or velocity?
Meter per second.
Yeah, speed, the unit of speed is equal to meter per second. So according to this relation, we can say that mobility is equal to mobility. The unit of mobility will be okay. Let us draw.
Meter square per volt
Meter.
second.
Yes, meter square per
Volt second.
volt second. Good. So in case of electrons, the mobility is higher, right? Okay. So now third point about the n-type MOSFET. So the first point is majority carriers are electrons. Second point is greater mobility, and third point will be the substrate of n MOSFET will be p substrate, p-type substrate. So we will let to know what is substrate. So that is positively doped. So if anyone asks you how many types of MOSFET, then you can say n-type MOSFET, and second is the p MOSFET. P MOSFET. So p MOSFET, if we talk about, then the majority charge carriers will be
Holes.
good. Charge carriers will be holes. Second point, if I talk about the holes, then the mobility will be less mobility. Okay, how can you understand the mobility? Let us talk about, if we talk about the the material, and here we will talk about the mobility. So there are two types of mobility, that is mu n and okay. So let us talk about, then you can understand. Okay, so let us talk about silicon. Okay, material is silicon. So in case of silicon, the electron mobility is nearly you can say, or 1380, that is centimeter square per volt second, and here also the unit is centimeter square per volt second. So for the electron mobility is 1380 centimeter square volt second, and hole mobility is mu p is hole mobility, so it is nearly 500. If I talk about the germanium, then the electron mobility is nearly 3800 and hole mobility is nearly 1800. Okay, so somewhere you can also see 1800 to 1900. Okay, so these are the two basic semiconductor material for which you have to remember the data, that is mobility. Okay, so this mobility is at room temperature. So room temperature means T is equal to 293.15 Kelvin. Okay, so you have to remember this data. So the mobility for the silicon and germanium at room temperature is, the whole mobility is 1380. Sorry, electron mobility is 1380 for silicon and whole mobility is 500. However, for germanium, the electron mobility is 3800 centimeters per volt second, and for whole mobility is for germanium is 1900. Okay, so less mobility. So in case of n-type MOSFET, we have seen that the substrate is p doped. So what about the p MOSFET? The substrate will be n doped, right? N-type substrate. So it will be negatively doped. Right. So now we will also discuss about the structure. Now next point we will discuss, there is a channel, there is a conducting channel, you can say there is a conducting channel between source and drain. Source and drain. So there is a conducting channel between source and drain. So the width of this conducting channel, or you can say inversion or accumulation, or you can say inversion, accumulation, and depletion will depend on the gate voltage, right? So gate voltage determines, or you can say controls, the flow of current in the device, right? So it means that the current in the device is modulated by gate voltage, thereby at age, that it is means MOSFET is known as voltage controlled device. So if I ask you in the exam why the MOSFET is known as voltage controlled device, then your answer should be like that: the current in the device is modulated, or you can say is controlled by the gate voltage, thereby the MOSFET is known as voltage controlled device. Okay, and how does it control, we will see later. So here, now one more important thing is known as the threshold voltage. What is threshold voltage? These are the basic term of MOSFET, so which is represented by VT. So what is threshold voltage? First point we will know that the threshold voltage is defined as the gate voltage, or you can say it is defined as the minimum gate voltage at which MOS device begins to conduct. So if I ask you, if let us say if gate voltage is represented by Vg is less than Vt, then what will happen in that case? MOS device will conduct or not?
Sir, it won't.
No, sir.
It will not conduct, right?
It will not.
Conduct means the device will not turn on, right? Good answer. So now we will see more about the threshold voltage. So at which the device begins to conduct, it means that turn on, right? Okay, now second point is that it is also defined as the gate voltage at which a strong inversion this is the mode of operation of MOSFET, inversion occurs. So we will also today about inversion. Now the gate voltage is positive for NMOS and negative, that is negative for PMOS. So we have to remember, whenever we design N MOSFET or P MOSFET, then we have to supply, or we have to keep the gate terminal positive for NMOS and negative for P MOSFET, right? Okay, so in the exam, if I give you some symbols or numericals you can see. So how can we people understand which, let us say, MOS transistor symbols? So by observing the symbols, you can identify whether the MOS transistor is NMOS, PMOS, or CMOS. So let us talk about the NMOS. So the symbol of NMOS is like that. Just you have to observe here. Okay, this one. So this is NMOS, right? So gate terminal will be, this is gate. Okay, and this is drain, and this is source. So according to the definition, what will be the value? What will be the this is gate terminal is positive or negative? It will be
Positive.
positive, right? And drain will be negative, and source will be negative, right? This is the first symbol for NMOS. Similarly, you can see right. Okay, and another symbol is like that. Like that. So this is source, drain, and gate. So, okay, now talk about the PMOS. Then you can easily differentiate. So in PMOS, okay, okay. So this will be gate, drain, and source. So what will be the sign convention here? It will be negative, right? Okay. So now another symbol will be like that. So this is gate, drain, and source. So as I told you initially, MOSFET is a symmetric device. Symmetric device means we can change the terminal of drain and source. So now C, that is CMOS, complementary metal oxide semiconductor field effect transistor, CMOS. So what is the symbol for CMOS? So we will see here. So you can see here. So we are providing, okay. Okay, so according to you, if you see the symbols of NMOS and NMOS and PMOS, then this is known as, what will be this one for this? So what is yes?
It's a PMOS.
PMOS.
Good,
PMOS.
good, good. And what about this one? It will be
CMOS.
no NMOS.
NMOS.
Sorry,
NMOS.
NMOS.
Okay, so this terminal will act as drain, and this will act as source. So about this device, we will look at it in more. We will look at it more in detail later. Okay, so now focus about, okay, so you have studied about the transistor, that is BJT, as a switch, right? So here also MOSFET also can act as a switch. So let us talk about here the characteristic switching, that is, if I talk about the switch, so far we have treated transistors as an ideal switch, right? So you have studied about the transistor as a switch, BJT transistor as a switch, as an amplifier. So you people have also done the experiment based on BJT? Right? Yes or no? So in the
On
third semester,
multisim.
on multisim you have performed the experiment. Okay, practically you didn't do that in the lab. Okay, no problem. So so far we have treated transistors as an ideal switches. Okay, so just talk about on. So an on transistor, what happens if the transistor is switched on? So an on transistor passes a finite amount of current, right? Finite amount of current, right? So the amount of current depends on mainly depends on two parameters, depends on applied terminal voltage, right? If you remember, if you increase the base bias voltage, then the current will increase, right? In case of BJT. Do you remember? Now, second point, the driving capacity of the BJT, our transistor you can say driving capacity, so derive current voltage, that is IV relationships, right? So now talk about the third point. So in case of MOS, there are mainly three terminals, right? Drain, source and gate. And one terminal is also, that is body contact, you can say. So BJT is a three terminal device. However, MOSFET can be a four terminal device, right? Okay. So for each terminal, that is for gate, source and drain, all have the capacitance associated with this, associated with them exactly. So MOS transistors, gate, source and drain all have certain capacitance. We will know how to calculate the capacitance. First, let us know the theory only. All have certain capacitance, right? So in the first year, you have studied about the amount of current flowing through a capacitor, or the voltage, amount of current flowing through a capacitor is given by I is equal to, anyone knows the formula to calculate the current flowing through the capacitor?
C dV by dt.
C
Good.
dV by dt.
C, very good. C dV by
dt.
So what is the physical meaning of dV by dt? Physical meaning of dV by dt is change in voltage with respect to change in time, right? So we can also rewrite these equations in the form of del V by del T, where del V represents change in voltage. However, del T represents change in current. Change in current, right? So we can rewrite these equations in such a way that, can we write delta T is equal to C divided by current multiplied by change in voltage, right? Can we write in such a way that?
Yes, sir.
Okay. So from this equation, what we can conclude? We can conclude that capacitance and current determines determines the speed of the device. The speed of the device. So if you remember exactly in case of BJT also, the capacitance play a major role in determining the speed of BJT if you have calculated the speed of the BJT of transistor. So have you calculated or have you heard about the term speed of the BJT?
No, sir.
Okay, no problem. No problem. We will discuss about it. You don't need to worry. Okay, so now, so this is all about the basics of MOSFET. So till now we have not seen the structure, right? So now we will see the structure of BJT. So here see, you will see the structure of a structure, that is a structure of MOSFET, right? Okay, structure of MOSFET. So as I told you, the MOSFET is a 4-terminal device, that is source, drain, gate and body, right? So let us talk about, we will focus mainly on NMOS. That is N type of MOSFET. So let us draw the 2D structure I am drawing, the cross section only. I'm not going to draw the 3D picture because my drawing is very weak. So here you can see, okay. So this is N plus, and here is the P substrate. P substrate, okay. So we can see, okay, the metal contact, okay. This is gate and here this is source and this will be drain, right? And here it will be ground, or somewhere it is also written as VSS. Okay, so now let us talk. Okay, so you may ask me, what is this one? This one is known as silicon dioxide, that is SiO2. So it will act as an insulator. Okay, so this is, and this metal contact, that is gate, is polysilicon. Polysilicon gate, metallic contact. Okay, so here what we can observe, this is N plus N plus. So what does it mean, N plus N plus? Okay, and this is known as length, this is known as channel. Okay, so the length of the channel is represented by L. So here what we can observe, so what does it mean, N plus? It means that heavily doped. Heavily doped. So always remember, whenever I talk about the heavily doped, let us talk about N region. So if simply given in the structure or in the data N region, so N region means the doping will be like that, 10 to the power 15 to, you can say 10 to the power 17 per centimeter cube. But if I say like that, N plus region, right? N plus region, it means that the doping will be like that, 10 to the power 18, so nearly 10 to the power 19 per centimeter cube. So this is known as moderate doping. However, this is known as heavily doping. Okay, doping. So what about what you will call the doping that is, let's say this N region is like that 10 to the power 14 to 10 to the power 15 per centimeter cube. It is known as low doped, right? So just you have to remember the range here. So N plus means the order of the doping will be nearly 10 to the power 18 to, you can say 10 to the power 20, you can say here 20. 10 to the power 20. Okay. So this is the structure. So we can see here an N-type MOSFET consists of a source and a drain, that is two highly conducting N-type semiconductor region, which are separated from the P-type substrate by reverse biased PN diode. A metal, or you can say polycrystalline or polysilicon gate covers the region between the source and drain, but it is isolated. Here, this contact is isolated from the semiconductor. This is semiconductor region, right? This whole region is known as semiconductor region. Semiconductor region. So this metallic contact is separated from the semiconductor region by an insulator, and this insulator is made up of silicon dioxide. So any doubt here? Yes? So since the region of source and drain is symmetric in nature, right? So as I told you earlier, the MOSFET is symmetric. So it means that any terminal, let us say this is a drain and this can be act as a source. So what will happen if you will change the length of the channel? So we will also study about it. So any doubt here in understanding the structure of MOSFET? Yes?
No, sir.
Okay. So let us talk about, okay, just write about it. Otherwise, if I ask you in the exam, then you can exactly write. So if I write about the theory, so let us talk an N-type MOSFET consists of a source and a drain, so that is two heavily conducting or heavily doped or highly doped, you can say highly conducting or heavily conducting N-type semiconductor regions which are separated from the P-type substrate. P-type substrate by reverse PN diode. Okay, so what does it mean? Okay, let us talk about this here. So this region is N type, right? And this region is P type. Okay. So here is N region, here is P region. So there will be a PN junction diode, right? Any doubt? So between the N plus region and P substrate, there will be a reverse bias diode. So the structure will look like this. Okay. Here also the same diode will form between the N plus region and P substrate region. So in P substrate region, what will be the majority charge carriers here in case of P substrate? What will be the majority charge carriers here? In P substrate region only.
Sir, holes.
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 And what about the minority carriers?
Electrons.
Electrons. Good. Why I am asking this? We will explain later. I will explain later. So first, okay. Now, second point will be a metal, that is gate terminal. I am talking about a metal, or you can say polycrystalline. Polycrystalline gate covers the region between the source and drain, but is isolated from the semiconductor region by the gate oxide, right? Gate oxide means silicon dioxide. So you can also verify it to the structure. So this is polycrystalline metal contact, right? This is separating from this region. This is semiconductor region by the silicon dioxide insulator, right? Okay. So next we will discuss about the
Sir, one thing I want to ask.
Yes.
सर वो उसमें डायग्राम में पॉलीसिलिकॉन क्या है, मतलब वो
It's a polysilicon or polycrystalline. This is a material. This is material, insulating material. Okay, this is, oh, you were talking about polysilicon, right? Yeah, this one.
Yes, sir.
This is polysilicon, or you can say polycrystalline. This is used to form the contact, to form the gate contact. This is metallic in nature. Okay, so whenever we form the contact, like this is like on the N plus region here. Okay, wait. Here, right? Here also contact. Here there is also contacts. This is also metallic in nature. So simply we can say this is metallic. Any metal you can consider, like gold, like silver, like Cu. But here for the gate, we use a special type of contact that is known as polycrystalline. The material used to make the contact is polycrystalline. But for the source and drain, you can use simply the metallic contact, that is either you can use gold, either you can use silver, etc. Okay, or you can also use aluminum. Now we will see the NMOS device behavior, or you can say mode of operation. Just I will take 5 to 10 minutes to explain this. So NMOS device behavior, or you can say the mode of operation. The mode of operation. Okay. So here I have taught about the NMOS, that is a structure of NMOS, right? So if in the exam, if I ask you to draw the structure of PMOS and explain the structure, then can you explain it? What will happen in case of PMOS? This N plus region will be replaced by
P plus,
and P substrate will be replaced by
N
N
substrate.
substrate.
So can you explain it
Um,
in the exam? Okay, it is very easy, just you have to understand. Okay, so now we will study about the NMOS behavior, NMOS device behavior, or mode of operation. So first mode is known as accumulation mode. Accumulation mode. Okay, accumulation mode. So just go back to the structure. So let us say this gate voltage is represented by Vg, and this source voltage is represented by Vs, and this drain voltage is represented by Vd. Okay, so now we can understand. So we have explained about the threshold voltage. So if the gate voltage will be less than threshold voltage, then in that case, let us say, okay, if the gate voltage will be less than Vt, that is threshold voltage, then what will happen in that case? That device will not operate, right? Will not turn on. That is true. So now we talk about the accumulation mode. So in accumulation mode, the gate voltage is less than 0. Okay. So what will happen in that case if the VG, that is gate voltage of the NMOS device, is less than 0? Then what will happen? We will see. Okay. Let us draw the circuit once again so you people can understand. Okay. So here there will be a N plus region, and here there will be a also there will be N plus region. So this is P substrate, right? So P substrate, okay, this will be a silicon dioxide here, and here it will be a gate contact. Okay, and here there will be a, so let us talk about, we are going to connect the gate voltage, it is less than 0. So here VG is less than 0. So let us talk about, here there is a P substrate, right? So P substrate means there will be a holes will be majority charge carriers, right? So let us draw the immobile ions here, that is positive. So what will happen in that case, we will see. Okay. So you are getting my point, whatever I am telling you. And this is channel, right? Okay, so what will happen in that case? See. Okay. So since we are applying negative voltage, so here there will be a negative charge, right? Any difficulty here? So this is SiO2, this is source, and this terminal is drain. Okay. So what will happen in case of here in accumulation mode, the VG is gate voltage is less than negative, right? So let us talk about the points. So because of the negative voltage, at the gate, negative voltage at the gate terminal, there will be a negative charge carriers there. There will be negative charge carriers will be there. There will be negative charge carriers there. What about the second point? Okay, so let us see here. You are applying negative voltage here, and here the substrate is P type, so that the majority charge carriers will be positive, right? So what will happen? The accumulation occurs typically for the negative voltage, where the negative charge carriers on the gate, and that attracts the holes from the substrate to the oxide semiconductor interface. So here, this is known as interface between semiconductor and insulator layer, right? This layer will act as a interface. That is there any doubt? This will act as a interface layer, right? Any doubt here? For in interface, this is known as interface between SiO2 and semiconductor. Okay, so what will happen? Here there will be negative charge carriers, and in the p-type substrate, the charge will be positive. So what will happen? It will attract just below the interface layer, right? Any doubt here? So here the positive charge carriers will accumulate just below the interface between the interface layer between the SiO2 layer and semiconductor layer. So there will be no formation of channel between the source and drain as a result, what will happen? The transistor will not turn on. So there will be no flow of current from source to drain. Right? Any difficulty in understanding this concept? Yes? Yes or no? Any doubt here?
No,
सर
sir.
इंटरफेस वो SiO2 वाली लेयर ही है ना?
Yes, yes, this is SiO2 layer.
हाँ,
This is
yes, sir.
insulator layer. So this boundary will act as a insulator layer, right? Sorry, interface, right? Here, this region is semiconductor, and this region is SiO2 layer. So this boundary will act as a interface layer between semiconductor and SiO2 layer. So what will happen, just because of this, the negative charge, whenever you will increase the gate voltage in negative direction, that is, let us say -2, -3, -4, -5, then what will happen? There will be a more negative charge carrier. So it will attract the positive charge carriers from the P substrates, and it will start accumulating just near the interface layer. So as a result, there will not be formation of any channel between source and drain. So thereby, what will happen? There will be no flow of current from source to drain. Okay? So can I move to the another topic? That is another mode. Right. Now the second mode is known as depletion mode. Depletion mode. Here the voltage is like that, the range of gate voltage will be like that. So here the gate voltage is positive, right? Here it is positive. However, it is greater than 0 but less than Vt. So what will happen in that case? The transistor will act, transistor will operate.
No, sir.
No, sir.
Exactly, it will
No,
not operate, right? Because still the gate voltage is less than threshold voltage. So what will happen in that case? Let us draw the structure so that you can understand. You have to understand the physics so that you people can write in your own language in the exam. So this is P-type substrate. Don't feel shy. If you don't know, say don't know. No issue. I am here to teach you all. But at least you should speak so that I also can understand that yes, you people are alive. Alive means you are present in the class. So this is N plus, right? Here there will be a SiO2 layer, SiO2, and this is here the metal contact, that is gate. Okay. Okay, so here the range is, okay, so this is source, and this is gate, right? Okay, so what will happen in this case? Now we are applying positive charge carriers, right? So positive voltage at the gate. So there will be positive charge carriers, and in the substrate also there will be a positive charge carrier. So what will happen in that case? The positive charge on the gate, pushes the mobile holes into the substrate, right? So what will happen? There will be a repulsive force between this positive charge carriers and this positive charge carriers, right? Because what was happening in case of accumulation, there was a positive ions here, right? In this region. Remember, in case of accumulation, what was happening? The positive ions was in this region, right? So due to the repulsive force, now what will happen? It will push the positive ions from this region, right? So the positive charge on the gate pushes the mobile holes into the substrate, right? So therefore the semiconductor is depleted at the mobile carriers at the interface. Now they are depleted, at the interface, and a negative charge due to the ionized acceptor ions is left in the space charge region. So this whole region now is known as, because now the immobile positive ions have been pushed back to the substrate. So this region is known as the depletion region now. Depletion region. Right? So why it is happening? Because of the repulsive force, right? Any doubt here?
No, sir.
Where you're getting gate, I guess drain will come.
Right? Sorry? Drain will come means? Okay. So one other very important term here, the voltage in the interview, in most of the interview, technical interview, they ask the voltage separating the accumulation and depletion regime and depletion regime is referred to as flat band voltage. So always remember, whoever are interested in attending the technical interview, flat band voltage. So which is represented by VFB. So now the third mode, that is the last topic, is known as inversion mode. Inversion mode. So here the gate voltage will be greater than VT. Okay. So let us talk about this region. So here the structure, again we will draw the structure, then we will understand. So, okay. P substrate. So here there will be positive, right? So again here there will be positive. Okay. So this is N plus, this is N plus. Here there will be silicon dioxide and there will be metallic contact. This is source. There will be a drain, this terminal. Okay. So here very important topic we are going to study. Just see here what will happen.
कान में क्या लगाया हो?
Hello.
Shit.
Please turn off your microphone. Right. So what will happen? This layer is SiO2, right? Okay. So now, whenever we now see, whenever the gate voltage will be greater than threshold voltage, so what will happen in that case? So there will be a positive charge at the gate terminal, and also because of the P substrate, there will be a positive charge here. So majority charge carriers will be positive. What were the minority charge carriers? What will happen in that case? This substrate, what will be the minority charge carriers?
Sir, electrons.
Electrons, very good. So in the depletion mode, there was a depletion region here, right? Here, right? But whenever you will increase the gate voltage, then it will start attracting the negative charge carriers from the P substrates, so which will start accumulating here because of the higher gate voltage, right? But still there will be some depletion here. Still there will be some depletion region here. And this is known as inversion region. So what is happening? So in inversion, there exists a negatively charged inversion layer at the metal oxide and semiconductor interface in addition to the depletion layer. So this inversion layer is due to the minority carriers that are attracted to the interface by the positive gate voltage, right? So you are understanding this concept, the inversion mode? Any doubt? So just quickly we will revise what we have studied today, right? So we have studied the basic fundamentals of MOSFET. We have studied the types of the MOSFET. Then we also studied the symbols of MOS transistors. Then we studied the structural details of the MOSFET and the modes of the MOSFETs. So what are the three modes of the MOSFET? Accumulation mode for gate voltage less than 0. Depletion mode when the gate voltage lies between 0 and threshold voltage, and the inversion mode where the gate voltage is greater than threshold voltage. So any doubt in understanding the physics?